Right now on Amplified, we're about to find out how to make a 3D scan of Dublin.
If people think that they have a good idea, they shouldn't give up. That if you push on it hard enough, long enough, it will happen. As crazy as your idea may seem, that a lot of times the best ideas are initially too far ahead of the curve. But don't give up on them.
Hi there, my name is Dusty Rhodes and welcome to Amplified, the Engineers Journal podcast. We're very familiar with BIM and LiDAR in civil engineering, but how far can you go with those technologies? Could you apply them to a full city and still get millimetre level accuracy? Our guest today is behind the world's densest urban aerial laser scanning dataset, which was conducted using a large slice of the centre of Dublin City. She is a pioneering force in urban data science, addressing the challenge of handling massive amounts of information collected by drones, satellites and laser measurements, and then using smart ways to store, search and turn that data into useful visuals. She is a qualified civil engineer, has authored over 160 peer-reviewed publications, been awarded 4 patents, worked as a professor in UCD Dublin, and is currently serving as a professor at New York University's Centre for Urban Science and Progress. I am thrilled to welcome Dr. Debra Laefer to the podcast. How are you, Debra?
Great. Thanks so much for having me.
It's a delight to have you with us. Before we get into the world's densest LiDAR dataset, which you generated here in Ireland, you had a very interesting route into engineering. You had a kind of an art history degree and then got into civil engineering. Tell me the story behind that.
So I fell in love with painting and old buildings and decided I wanted to become an art historian. So I applied to the best program in the United States and got admitted to Columbia University. And as part of this, I got involved with creating a student art gallery. So this was supposed to be a place where students and faculty and alumni could show their own artworks. And then we were informed that we had to temporarily move out of the space because they were going to do construction through it to put in some new telecom lines. So this was back in the mid to late 80s. And I was concerned because it was a historic building. So I started asking around, started doing some investigation, and found out that not only was it a historic building, but it had been damaged. In fact, it had been damaged the last time they did construction near it. So called the landmarks preservation people to confirm that, yes, the building was protected. We reached out to people at the historic preservation program at Columbia University, and they put me in touch with one of their students who is a civil engineer. And I was so impressed with this young woman. Her name is Marie Ennis. She's actually still a practicing engineer here in New York City, and that she could combine this large toolbox of thoughts and knowledge and convey it in a way that was meaningful to people in practice. And I was very, I think, influenced by that. And over the next few months, I started thinking, well, if I really love old buildings, maybe this is what I want to do. Maybe I need to become a civil engineer. So there I was, finishing my last year in my Bachelor's of Arts degree in art history and starting my first year in my Bachelor's of Engineering in civil engineering. And ultimately, I persevered with this. I've been worked in the construction industry at a time where it was pretty rough. A lot of organized crime, a lot of violence on the sites. It was a pretty exciting time in New York construction. But I was happy doing that. And I thought, oh, well, I feel like I still don't know enough. So why don't I start a master's program at night part-time? And as part of that, I met some amazing people in the geotechnical engineering realm. So that's a division of civil engineering. And a lot of them, surprisingly, had PhDs. And they were in the midst of really importing a lot of amazing technologies from Europe into the United States. Things that were very well suited to protect existing structures when you did excavation or drilling or blasting or dewatering or tunneling near them. So I finished my master's degree. I applied and got a Fulbright to Italy. I spent a year at the Politecnico in Milan, really studying brick masonry and its vulnerabilities. And then I came back to the US and I took my PhD in geotechnics. But I had also the opportunity to do some traveling as part of that research. And we went to Korea, and I got a chance to come over to the UK and to spend some time, particularly with some people from Mont MacDonald, looking at the Jubilee line. So at the time, this was the most expensive tunneling project that had ever happened. It was about, I think, £2 billion. And about 25% of this was being spent either on predicting which buildings were going to move, monitoring them, or, kind of pre-tunneling intervention, where they were pumping grout under the ground, in particular under Big Ben. And despite this huge investment, a lot of buildings did get damaged. So when we spoke to the engineers, we said, well, what kind of great computational models are you using to predict which buildings are going to get damaged? And they said, we don't use the computational models. I said, what's wrong with them? And they said, no, because there's nothing wrong with the model, but we do not have documentation of all of the above ground buildings. I mean, many of these buildings date back hundreds and hundreds of years. And to go out and to survey each building and then convert to generate drawings, and then to convert that into a computational model would be impossible for the hundreds and hundreds of buildings that are along this tunnel route. So instead, we're using a fairly simplistic set of numerical equations that date back mostly to the 50s, and then kind of improved in the early 70s. So here we are, we're pushing the turn of the millennium, and we're using stuff that's at least 30, if not 40 years old.
So that I understand it, you find yourself in London and you have all of this tunneling going on. They can't correctly tunnel because they can't do the computations for all of the buildings because it's just too big an area.
It's not that they can't tunnel. They can tunnel, but it at greater risk to the structures than need be.
So you said to yourself, aha, here's a problem. I'm going to come up with a solution for this.
Not quite. I just went home and thought, wow, I'm surprised. This is a problem.
Yeah.
So I went back, I finished my degree, and about 2-3 years later, I had just finished. I had moved to North Carolina to become a young faculty member, and 9/11 happened. And having spent many years in New York studying and working, having much family there, my parents were born there, my grandparents were born there, many people from our family still live there. It was a very disturbing and moving kind of time. And I was very interested in what they were doing, how they were trying to do the rescuing, because I'd been involved with some kind of post-disaster earthquake work while I was also at the university. So I was kind of a little tied into the emergency management community at that point. And I started to learn about a fellow named Dave Bloomquist, who was a faculty member down at the University of Florida in Gatesville, and his work with NOAA and the work that they did to basically put up a small plane and to do heat detection and LiDAR over the World Trade Center disaster zone so that it could help them both figure out where there might be fires happening underground still and how to start to remove debris. At that point, they already realized that there were probably no survivors. So, I started looking at these 3D models or 3D representations using this LiDAR data. And I thought, wow, that's really interesting. And about 4 months later, I was up in New York and I had an opportunity to work, to get to know an engineer who was really helping coordinate a lot of that removal and had the opportunity to actually go down into the site. So this is like January 2nd, 2002, and the site is still on fire. Even with a gas mask, it was very hard to go through. But I'm looking around and I'm seeing, these buildings and the damage and thinking about the work that Bloomquist did. And I said, wow, maybe we could use LiDAR to document all these structures. So I called him up and he was very generous and he helped share some of his experience and helped get my group started. And we started doing some work in this area. And we started doing some work for the Illinois Emergency Management Agency, looking at prediction of trees falling across roadways, where we would go and from the LiDAR they already had, we could measure the height of the tree and the distance to the road and make estimates to what extent, if the tree fell over, it would either partially, completely, or not at all block the road. So that was kind of our first foray into that. And once I started, I was completely hooked.
Okay, so now it sounds like you are looking for data over huge areas of land and very highly populated land with a lot of buildings in it. That's a huge amount of information that you need. LiDAR piqued your attention. For engineers who are not working in this space, can you explain how that technology works? How do you 3D scan an area?
Yeah, so it's a technology that can be used from multiple platforms, even from right now from your iPhone. Or from some type of stationary unit. The unit can be mounted on a car. It could be small ones can be mounted on drones, on helicopters, on airplanes. The technology is fundamentally the same. You're sending out a laser signal, kind of a beam of light. You know what time it left your piece of equipment, and you know where kind of in the world your equipment is. Is it on the ground? Is it above? Is it at the bottom of Grafton Street? You know what angle it's
at. Yeah, the bottom of Grafton Street.
Right. So that beam, part of it will come back. It will hit something and it will come back. And you will know, and the equipment will record the time that it comes back. So based on the change in time, we have a certain distance that can be calculated because we know what the speed of light is. And we use that to determine what they call the range.
And you were doing this millions and millions, I imagine, millions and millions of times a second.
Yeah, I mean, ultimately, obviously some of it's limited by your equipment, but it's actually more limited by how much data the equipment can take back and how long your battery is good for.
Let's put a picture on it, okay? You somehow found yourself in Dublin and you decided, Grafton Street, okay, we're going to 3D scan that and we're going to measure that down to, what kind of measurement did you get it down to? What scale?
The first scan we did was about 4 centimeters.
Wow. Okay, all right.
And the second, I think, was down to about 2.5 centimeters.
Wow. So tell me.
Maybe actually even less than that. So maybe about a centimeter.
Tell me about this story about how you used helicopters, drones, whatever, centre of Dublin, Grafton Street, the whole block, and you measured it and 3D scanned it to within a centimetre.
So what we really wanted to do was to provide these representations of these buildings to the engineering community. So you have to set your mind back to 2004, Celtic Tiger, Ireland's booming, and a lot of discussion about putting in Dublin's first metro to go from the bottom of Grafton Street, or more specifically, in the northwest corner of St. Stephen's Green, up to the airport. So Dublin and Ireland in general at that point had almost no tunneling. And obviously here we are in a country that has limited experience with this technology. You have a very complicated geology with a lot of small granular material mixed in with kind of big boulders and stuff. So it's a tough thing to tunnel through without a lot of disturbance of the ground. And here you have this amazing architectural resource in terms of the center of Dublin that at that moment was actually under consideration as a World Heritage Site. So you had this kind of conflict happening about preserving and the future and at risk. So I was fortunate to put together a proposal to Science Foundation Ireland with a colleague at UCD Dublin, Hamish Carr, and a colleague up at, our collaborator up at Trinity. We were able to come up with kind of a plan of not only how to acquire this data, but how to process it and make it usable.
Okay, tell me about acquiring it.
So when most people, even today, put this kind of unit under a plane or a drone or a helicopter, it faces down. So the unit swings, and depending on the equipment, it might swing just left to right, or it may have kind of an arc to it. But it's kind of, it's not just capturing exactly what's below it, but kind of a swath. But it's pretty much focused on what's directly underneath. And as the LiDAR unit swings to the side, the quality and quantity of data that you get when it intersects a building facade is pretty limited. So most of the good data that you're getting is of roads and roofs. But if the thing that you're interested in knowing about and protecting is the building's facade and its structure, knowing about its roof and knowing about the street next to it's not going to help very much. So we kind of took a big step back, and Hamish and I were really like, well, how do we capture these building facades? And we said, well, let's think about the equipment. How does the equipment work? And how do they traditionally fly? Well, even a old kind of medieval city like Dublin has a kind of pattern to it, and much of it's a grid. So typically what they do is they say, okay, we're going to fly from X to Y and from A to B. This is our kind of area. And they will fly along the grid line. They'll go down, turn around, back, down, back. And then when they're finished with that, they'll come around 90 degrees and do it the other way. It's great for the pilots. They rarely get lost. It's not so great for the data acquisition for the kind we wanted to do. So we showed through geometry that if you flew diagonal to the street grid, that you could pick up significant, like basically double the information.
Just because of the angle.
Just because of the angle. The other thing we realized is that the amount of overlap that they fly was only enough to basically sew together, one group of data from the next. So when you're flying down one street, they would go over, they wouldn't necessarily do the next street, that they would position themselves so that there was only about a 10% overlap. So if you're from the geomatics community and you're interested in mapping and you're interested in floodplain or using this for floodplain risk analysis, this is great. But if you're interested in looking at these facades, it's not so great. And it basically really limits what you can pick up because it's in that swing at the edge of the scan that we're picking up the facades, right? Because when we're looking down, we're looking at the street, and now we're swinging to the left, and only at the end of that swing do we start picking up that data. So again, we went back to basic geometry and established that we needed about a 60% overlap to achieve a complete scan so that we didn't have these basically blank spots. Because you have, with this line of sight technology, if you can't see it, you can't capture it, like with a camera. So you have a situation, if you're standing in front of a building, you obviously can't see what's on the back, but also sometimes buildings preclude you seeing a building behind them. So if you're up in the air and you've got a tallish building and maybe there's a small one across the street, maybe you can't see that. So again, we had to kind of compensate for a lot of these things. When we originally bid this, people thought we were insane. They're like, why do you want to do this? And we're like, trust us. And it was very hard to even find a contractor to do it. And when we got the data, they were astonished. They're like, wow, we had no idea we could get this kind of data.
Let me just say that there is a YouTube video of the data that you got. And when you watch the video, your jaw will drop and go, oh my God. And I have put a link directly to that video in the show notes in the description area of this podcast that we're listening to right now. So you can just click on it and you can see it. Apologies, Debra, go on.
No, thank you. I think that's one of the best demonstrations of it because we didn't devise a sensor. We didn't even improve the sensor, but we took a fundamentally engineering approach to it. So I think that the way the technology had been used, this idea was like more data is better. And you just get what you can and you smash it together and you kind of muddle through the best you can. And we took this more systematic approach of let's reverse engineer the process, figure out what we want to get, and figure out how to use the sensor to obtain that data.
So now you have the data, but the problem is that you have an enormous amount of data. And that's the next problem, the next challenge. What do you do with it? I mean, how do you sort those many ones and zeros?
Yeah. So the basic storage of it, the what we call the static storage, just, putting it somewhere is not so much a problem. My brother used to work for Google and he would joke, what's a petabyte between friends? So it's not the storage. It's as you said, it's the sorting, it's the what they call the querying, it's the retrieving of the data. And so we really, with my help of my long-term colleague and collaborator, Michela Bertolotto at UCD, really sat down and looked at a lot of the work that she had done in database and database structures and talked about, well, what were our needs? How is the community currently doing at least some of this work? And what was that opportunity? And so in about 2006, we really started in earnest taking on that problem. And I would say that work really culminated about 9 years later when we jointly graduated a PhD student who demonstrated that you could very effectively use the data structure as the fundamental building block for post-processing algorithms, so that you already have stored the data in a way that is highly usable. The paper that An Vouveau, our joint graduate student who is still in Ireland, is the lead author on, is in the top 0.01% of all papers cited for the year it was published. This technique has been used in fields as far from civil engineering as breast cancer research. So that not only has it been transferred to other LiDAR applications, but people have used it for other remote sensing and medical imaging data sets, so which is really amazing.
So you put some manners on the data, then how do you integrate it with other technologies? So a lot of people talk about GIS and BIM and stuff like that. How do you get that data then interacting with them so engineers can actually use it?
Yeah, I would say actually most of the ways that engineers use it are actually in computational models. So certainly there are ways to tie it to GIS systems. The time we were working, there wasn't even a full 3D solution, which meant that it was what they call a 2.5D solution, which means that every Z point, every elevation point, there could only be one unique one for every XY point. So if you had a building that was truly straight, there was no way at that XY point, at that corner of your street or the corner of your building to represent both the bottom and the top. So you had this kind of slightly wedding cake effect where the points were actually slightly offset. Obviously, the technology has moved on from now. These GIS systems can both produce and host 3D models. But just to give you a sense of kind of where we were, with this, BIM kind of really wasn't even really a thing by then. And the challenge is that unlike a photograph, when you have a photograph and you look at it, every pixel, every little space is filled, right? There's no blank spots. With the LiDAR data, it's not that way. Maybe the beam went through a window and it didn't come back, or, maybe it went through a tree and it came back in like 6 different pieces. So you get this data set that's very non-homogeneous. It's often referred to as sparse. It's unordered. So there's no natural order when you get it back from the vendor. I mean, it's been georeferenced, but it doesn't like say, oh, this point belongs to a building and this other point belongs to a building.
It's a bit scattered.
It's a bit scattered. It's a bit chaotic. So we continue to pioneer really, it's a groundbreaking work in how to fundamentally store that data, because very early on, it became clear that the sheer size of the data, it was a major impediment to people using it. And it still continues to be. So some of my most recent work that we've not published yet really looks at how do you take 1 billion points and process them actually just on a regular PC? Can you do that? So for us, the bigger question was, how do you get these points into a computational model? We don't care if we're labeling them necessarily. I mean, eventually you want to label them to a certain extent because you want to know if your material model for each piece is correct. But the bigger thing is, how do you generate what they call a watertight model? And this is where the 3D printing starts to sneak in. So to do a computational model, you have to create what they call a watertight mesh, which means that every point has to be connected to other points through a set of lines. But these lines must connect at nodes. They can't overlap. They can't be a little short of them, right? And when you use the traditional transformation processes that were available, particularly in the late 2000s, you ended up having to do a huge amount of manual correction. And if you're looking at a terabyte of data, that's not going to work, right?
Yeah.
So we really had to kind of think about, how do you overcome those problems? And through this wonderful kind of collaboration between computer science and through civil engineering that we had going on at UCD, between myself and Hamish Carr and our students, Tommy Hinks and Lin Trung Hong, we had this kind of eureka moment that the way the computational models were set up, many of them used what looked like almost little bricks, that they were these 8-noded elements, and that these 8-noded elements, which didn't have to be squares, they could be rectangles, looked an awful like the elements that we were using to do the storage.
Excellent. So this is acting like a key, is it?
Yeah. So we divided the data in something called an OCT tree. So where you chop it up into basically 8 quadrants. And if there's no data in the quadrant, you forget about that part. And then you keep kind of digging down, either until you only have a certain amount of points in a box. Maybe that's the amount of points that can be stored in the computer's cache and dealt with comfortably, or maybe you do it more generically and say you're just going to do, 5 divisions of these things. And we realized that the OCT tree and the computational model in the finite element, they looked a lot alike. So then we came up with 2 really pioneering algorithms to do that transformation. So as we were thinking about watertight, so what is starting to happen? The patents for the original 3D printers are expiring. And we're starting to see this boom of 3D. So actually, this is about 2012, 2013. Started to see this boom of home 3D printers, or low-end 3D printers. There's 3D printers this, 3D printer that. People are even talking about, maybe can you 3D print a house? All these things that people are now really excited. In the same way, everybody's talking about AI now. So if you cast yourself back to 2013, everybody's talking about 3D printing. They're 3D printing clothing and hats and everything. And we start saying, well, if we're creating this watertight model, couldn't we use that same watertight model approach for 3D printing? Because that's what you need. The input files for 3D printing have to be these watertight models. So there was an opportunity to apply for a competitive commercialization type grant through the EU. At that point, I had received the European Research Council Award, which was the single PI award that you could obtain at that time. And they had a program, they wanted to really try to commercialize work. So you could then say, okay, this piece of work came from this project, and we'd now like to try to commercialize it. So we went through that competitive program, and we got a good amount of money, and we said, okay, we have this wonderful used 3D printer, commercial grade metal 3D printer that we were able to acquire. And it quickly became apparent that this is a very expensive thing to run. It requires a huge amount of knowledge that you have to keep in the group. And we said, how are we going to sustain this? So we said, well, there's no 3D printing centers in Ireland. What if we opened one? So that was our next big adventure. And we started to acquire other funding and other equipment. And we really, kind of graduated a whole class of people who then went on, many of them, to really lead the introduction of what are called advanced manufacturing in Ireland, including a guy named Brian Marin, who came to us off the dole through a, train to work program. And it was so successful that Brian became the main initial technician for the first National Advanced Manufacturing Center. So I think a real success.
Let me put this into some kind of a context then on the engineering and design side of things, because we're used to BIM and we're used to digital twins and you're able to play around with buildings and change things and see how it looks. How can you do that? Can you use this technology that you are working on to do that on a citywide level?
Yeah. So obviously acquiring the data takes a while, processing the data. So it's not something that you just go out and do every day. But we do see that communities, municipalities, even states are doing this now on a pretty regular basis, if not once a year, once every 2 years. In fact, in the United States, we are having the completion of our first national scan, which is pretty exceptional. The difficulty of processing and storing that data is in part related to the quantity of the data. If you want really good sub-centimeter data, it's going to be a lot. So that always has to be part of it. But we have certainly taken that data and we've, generated little 3D models of parts of Dublin.
And where would an engineer be able to use that if he is looking as a city planner? What kind of things would he be able to do with it?
So I think one of our very early visions, particularly when we got our first data set back in 2008, we said, this data is so good, but it's not quite good enough. That I think the aspiration was to have a data set that was so good you could pick out the curb height.
Wow.
And I think that is what we really achieved in 2015, that the data was so good that we could determine basically whether the edge of the sidewalk was handicapped accessible. So I think that's a very easy, accessible use case. We've now most recently we just completed a project called Urban Arc with UCD and with Ulrich Offendinger up at Queen's University Belfast, looking at urban flooding. And one of the key components to that was the detection of subsurface spaces, basements, parking garages, things like that. And although LiDAR is a line of sight technology, we can get a pretty good understanding of some things, that there are these spaces and to some extent the size of them. Based on if you're, the angle you're collecting the data, you might see kind of the stairwell that many of our Georgian townhouses have, or even be able to capture some of the data through the windows or the entrances to parking garages. And by incorporating that into a larger flooding model, we can determine more effectively where the risks really are. Where is the water going? Are we over-predicting? Or these people are particularly at risk? And we've generated flood models that show that these subsurface spaces really have an impact of where the water's going and how fast it's building up. So if you're trying to evacuate parts of the city or deploy emergency services, you want to know where to do that. You don't want to send people to the wrong places.
So listen, you've done Dublin City. I believe you're going for something slightly bigger for your next project.
Not so much bigger, but maybe more technically advanced. So we've recently completed a 1 square kilometer area in Southwest Brooklyn. And what's really special about that data set is not only do you have this great LiDAR data, pretty much the equivalent of what we did in Dublin, a little bit denser, but we've coupled it with something called hyperspectral data. And hyperspectral data, ours is in the bottom of the short wave range downward. So if you have materials that are known and you can get what they call the spectral signal from them, we can match that spectral signal with things in the built environment. So a computational model has two important components. One is the geometry, and that project through our lab work and those of others has largely been solved. But the assigning of those materials and those material properties has not. And hyperspectral gives us that opportunity to start doing that. So some exciting stuff happening.
A lot going on. I love talking to you because you're talking about things you did 20 years ago that are almost like cutting edge now. You have the type of brain that just thinks 20, 30, 40, 50 years in advance. So I have to ask you, what do you consider now the main challenges that engineers today need to start thinking about?
I would say one of the main challenges is coupling these major weather systems or storm systems with that kind of urban level weather system. We have huge investments of, trying to predict where hurricanes are going and how much rain and how much storm surge. But what's really happening from the street level, say, up to the first 100 or 2 feet? There are not a lot of models. And yet all of that's controlling all these urban heat problems that we're having. And we just don't have those coupled models. So it's that multi-scale physics that we're kind of missing right now, where people like me, very much on the ground at the bottom, could work with somebody like one of my collaborators, Olivier Police, here in our chaos group, which is our weather group in our math department. Between Olivier and myself, there's a big space. And there's not too many people in that space. So I think that's really where we need to start going.
I also wanted to ask you, because I was watching an interview with you and you were talking about the advice you give to your students, which, it just rung true with me. It's when you're a student, make mistakes because you learn more from mistakes than when things go right. Now, that's great to say to students. We're all engineers listening to this podcast. Can you apply that to engineering in a real life professional situation, or should you just have made all your mistakes in college?
One of the highlights of my educational career was getting to meet a geotechnical engineer named Ralph Peck. And Ralph Peck at the time was the most important living geotechnical engineer in the world. And he had been a student of Carl Terzaghi, who is the founder of geotechnical engineering. And he would come at the age of, 79, and he would give these talks about when he was a young engineer working under Carl Terzaghi and all the mistakes that he made. So it's good to make mistakes, and it's good to have senior engineers check them.
Keep trying new things regardless.
Yeah.
Can I wrap up then by just asking, is there anything else that you'd like to add to our chat today that I haven't thought of or haven't brought up?
Yeah, I think that if people think that they have a good idea, they shouldn't give up. That if you push on it hard enough, long enough, it will happen. As crazy as your idea may seem, that a lot of times the best ideas are initially too far ahead of the curve. But don't give up on them.
If you'd like to find out more about Debra and some of the topics that we spoke about today, you'll find notes and link details in the description area of this podcast. But for now, Professor Debra Laefer from NYU's Centre for Urban Science and Progress, thank you so much for an absolutely fascinating chat.
Lovely to be here. Thanks for the invitation.
And if you enjoyed our podcast today, do share with a friend in the business. Just tell them to search for Engineers Ireland in their podcast player. The podcast is produced by dustpod.io for Engineers Ireland. For pre-released episodes, more information on engineering across Ireland or career development opportunities, there are libraries of information on our website at engineersireland.ie. But for now, until next time, for myself, Dusty Rhodes, thank you for listening.